So I would like to talk about some work that we've been doing in my lab over the couple last years, which really kind of tries to address what happens as the rocks cross the brittle-ductile transition to the microscale defects that enable deformation. And this is work, of course, done mostly by people in my group. Hamed Ghaffari, who's a research scientist who did the lion's share of this work, Uli Mok, who's the lab tech, Tushar Mittal, he was a postdoc at that time at MIT, who did the analysis of the data. Hilary Chang, who was a PhD student who also analyzed the acoustic data, and Brian Evans, who helped us with the overall his great knowledge of Carrara marble. So let's get started. So first, to get everyone on the same page, what are brittle ductile transitions? So here we see a view of the Earth with plate boundaries illuminated by earthquakes. And if we take a cross-section from A to B and look what the cross will look like, and we will focus far away from all the complications of active plate boundaries like subduction zones, the idea of a brittle to ductile transition zone seems simple. Rocks at low pressures and low temperatures close to the Earth's surface will break and therefore deform in a brittle manner, whereas rocks deep in the Earth at high pressures and high temperatures will flow and therefore will deform in a ductile manner. So that implies that there must be some transition from this brittle behavior to this ductile behavior as the pressure and temperature, and therefore also depth, of course, increases in the Earth. So that seems fairly simple, right? So why do I use plural? Well, it's because the concept of a brittle ductile transition is common in many fields, but may have very different physical origins due to the vast length and time scales over which it occurs. So for example, if we start with earthquakes, as shown here on the kilometric scale, then we can see that earthquakes along the San Andreas Fault sort of occur mostly in the upper 10 kilometers or so. After that, we have some slow slip events that go down to about 30 kilometers depth. And after that, we don't detect any earthquakes anymore. And so that would imply that if the earthquakes are related to breaking of the crust, then they are prevalent on the surface as expected. And somehow we transition from this breaking to a more complex region until we get to this flowing region again. Now, if we go to smaller length scales and look what is it that we can see in the field in structural geology, we frequently observe the intercalation of faults and fractures with mylonites with multiple cross-cutting relationships, indicating that the rocks experience both brittle as well as viscous deformation or ductile deformation. And so therefore, it appears that at this length scale, both processes can co-occur. Now, in the laboratory scale here at the millimetric sample size, the definition of a brittle ductile transition is such that if we deform initially intact rock and we see that a fault developed, then we call this deformation brittle. And if we see that the sample barreled and there's no obvious macroscopic localization into a fault, then we call this deformation ductile. Now, the localization of strain along faults is one of the prerequisites for earthquakes and for rapid motion along faults, but not all faults need to generate earthquakes, and can also occur during slow creep processes. So the link between localization along faults in experiments and, for example, seismicity, as we see in nature, is not straightforward. And I'll stop at this scale for now, because most of the talk I'll spend talking about the smallest scales and what is it that we can do in the lab. But I just wanted to get everybody on the same page and talk about the broader perspective. And so why would we want to study the brittle to ductile transition if it's so complicated? Is it hopeless to study, or where would this problem actually matter? And here I have just 3 examples where understanding of brittle ductile transitions is really crucial. The first one is in applications to deep geothermal energy. So right now we are in the middle of an energy transition where we need to phase out all carbon-based fuels as quickly as possible. And that will require massive changes to our power grid. We need to build up renewables, but we also need reliable carbon-neutral baseload power. And this can be basically currently achieved only with nuclear or potentially with deep geothermal power plants. So we need to learn how to drill, maintain boreholes stable, and flow fluids through rocks at high temperatures and high pressures, where interplay between brittle and ductile deformation will be crucial to understand. A more fundamental question relates to the strength of the lithosphere. Here we see the famous jelly sandwich model of the strength of the lithosphere, where we see here differential stress plotted on this axis versus depth. And we see that as we increase the depth, then the strength of the rocks increases following the frictional law of Byerle's for frictional sliding, until we get to some depth at which it becomes easier to flow based on some flow law that is appropriate for the mineral that is at that depth. So for example, here we first transition from frictional sliding to flow of quartz, and as we go to the lower crust where feldspar seems to be the dominant mineral, then we transition back to the frictional sliding until we hit again some olivine flow law. And the exact transition, how we transition from this frictional sliding to this viscous flow is kind of not well constrained, and that's where the brittle ductile transition is occurring. And of course, this is a very static view of the strength of the lithosphere, and the strength of the lithosphere evolves over the earthquake cycle. So here on this last plot, we see what this strength profile could look like during the whole earthquake cycle. So the first blue line shows us what the stress in the crust is before the earthquake. And here this blue line shows the displacement on the hypothetical fault. So you can see that we have the deep creeping crust. We have some locked segment, which is building up the stress. And during the earthquake rupture itself, we need to somehow dynamically weaken this whole locked patch and accommodate all the slip deficit that has accumulated over the tectonic loading during the co-seismic slip. And so that would then correspond to this orange line. So we need to somehow weaken this rock. And then as the earthquake ceases, then the strength again recovers and we return to the original strength of that rock. This will mean basically the transition from some viscous flow and brittle deformation will be occurring over a large interval of depth and very intermittently within the earthquake cycle. And so where can we start in this problem? So we can start at the smallest scale, where basically we can look at what the microscopic defects do. So if we start really small, then we can quite clearly define what is brittle and what is ductile. So microscopic defects are basically fundamental agents of deformation. They are cracks, for example, dislocations, grain boundaries, point defects, and so on. And depending on their activity and interactions, the rocks will either break or flow. So here is a hypothetical kind of evolution, how the defect activity in a hypothetical rock could evolve from a low pressure and low temperature to a high pressure and high temperature. And here we have how much of these individual defects are taking up the strain rate. So if all the deformation is accommodated by cracks or by cavities, which are basically all defects that have some positive dilatancy, so they have some positive change in volume as they form, then we would call this deformation brittle. And if we have all just volume conserving defects as dislocations or twins deforming the rocks, then we would call that ductile. And how exactly this transition occurs is, of course, generally not too well constrained. So any behavior which kind of has a combination of these brittle defects and this ductile defects accommodating together the deformation is typically called semi-brittle deformation. And it's a very common mode of deformation that is seen in many rocks. So this is an example from a deformed marble that was deformed at 25 megapascals confining pressure and 23 degrees C. So 25 MPa confining pressure corresponds roughly to about a kilometer depth. And what we can see here is that there's a lot of cracks, which are here, these black kind of more tortuous lines. And we see also a lot of these very straight lines, which are basically slip lines. So either those are very thin twins or those are planes where a lot of dislocations propagated through. So clearly, both of these defects were active and helped to accommodate deformation during the experiment. Now, we see similar microstructures also in quartz, but of course at much higher pressures and temperatures. So this is an example from quartz deformed at 1.5 GPa confining pressure and 900 degrees C. And those are cathodoluminescence images where the cracks beautifully pop up as blue, and the slip lines and crystal plastic feature in the quartz grains appear with these kind of brightish yellow colors. So we can see that a similar process is also occurring at much higher pressures and temperatures in quartz and helps to accommodate strain. So let's start at the now at the lab sample scale, or we worked our way to the lab sample scale. And this is essentially the original length scale at which the brittle-ductile transition was first defined. So as I told you in the beginning, the definition from an experimental point of view is that if I deform my rock and have a through-going fault, I'll call that brittle. And if I deform a rock and it just barrels, then I'll call that ductile. We collect also all the mechanical data on this scale. So the yield criteria and flow laws and so on, they generally come from samples that are on the centimetric scale. And one of the problems is that localization along a fault can occur by both brittle as well as ductile micromechanism. And distributed deformation can also occur by both brittle as well as ductile micromechanisms. So the transition here from what the individual defects are doing to accommodate the strain in the rock and what is then happening at the larger scale is not obvious and generally not easy to unravel. So now, why does that matter? Is that the typical brittle ductile transition, essentially defined on this length scale, comes from experiments where we increase the confining pressure, which is shown here on the x-axis, and we measure the shear stress that is necessary for the rock to start failing, basically the peak strength that it can reach. And here what you can see is that we have essentially three different failure envelopes that are plotted. The first one is the Byerlee's rule for frictional sliding. So that just quantifies how much shear stress is needed to slide a pre-existing fracture. And that will become harder and harder the higher the pressure is, because we're pressing with more and more normal stress on that fracture. And so it needs more and more stress to slide a pre-existing fracture. Now, the second envelope is the so-called failure envelope. So that is applicable for intact rocks. So if we take an intact rock that does not have any fracture in it, then we typically have to first get to a stress where it fractures. And that stress is also increasing with increasing confining pressure. But eventually we will reach the peak strength of the material where the strength will become largely independent of pressure. And so there is some intersection here between the Byerlee's rule and the failure envelope of the intact rock, which basically tells us that at this point, it will become easier to fracture the intact rock than to slide an existing fracture. And that's where the brittle ductile transition is defined based on these macroscopic data. And after that, we're entering this semi-brittle flow field until we reach this so-called intersection, which is called sometimes the brittle plastic transition, where we intersect this failure envelope with the Goetze's criterion. The Goetze's criterion is just an experimentalist rule of thumb, which basically says that if the differential stress is lower than the confining pressure, then you are likely deforming the rocks by some crystal plastic processes. And so once the differential stress is lower than the confining pressure, then we're in the fully plastic field where basically deformation tends to be strain rate and temperature dependent, whereas in the brittle field, deformation is mostly pressure dependent. The issue with this is that despite decades of work, failure envelopes are largely empirical in the brittle field, and only a few micromechanical models exist that would allow for better extrapolation. So determining where exactly this transition is in terms of intersection of this Bayerle's rule for frictional sliding and failure envelope is not trivial, as the failure envelope will depend on the temperature, rate, and other parameters. So the question is, what is it that we can achieve in the lab? So what we can do is that we can try to connect these microscale defect dynamics to the grain scale defect dynamics, and then to the sample scale. And given that there is already quite a vast range of length scales and time scales, we need to collect some observations that are broadband and ideally in situ. And so historically, what people have been doing for quite some while is collecting the mechanical data, which is collected over the length scales of millimeters to centimeters in the sample. And typically the sampling rates are somewhere around 1 sample per second. The microstructural data, which is appropriate for characterizing the microscale and the grain scale in terms of length scale, can go down to angstrom, so we can basically image individual atoms. But the downside of microstructural analysis is that typically we can only have a snapshot of before and after deformation. And so it's difficult to see how exactly these defects are moving. And what we've been working on in my lab over the last 5 or 6 years is that we were developing ultrasound probes that basically would allow us to bridge these length scales and sample on the millimetric to micrometric length scales and at frequencies in the tens of megahertz regime. So we can resolve how these individual defects are actually moving and connect these observations a little bit better. And we have developed some machines that we can kind of instrument, and miniature sensors which we can put into the machine so that we can record these acoustic emissions. And this has been spearheaded by my research scientist Hamid Ghaffari, and greatly helped by Uli Mok, who's our court technician. And so the experimental setup that we used for this study is that we use Carrara marble, which is a very classical material for studying this brittle-ductile transition, because it goes through a brittle-ductile transition at room temperature, which makes it in many cases much easier to instrument. We use the Patterson gas medium deformation apparatus, which allows us to go from pressures of 0.1 to 300 MPa, which is sufficient to cross the pressure range that is needed to cross the brittle-ductile transition in marbles. And we use these ultrasound probes. We have basically 2 sensors which are sitting right on top and below the sample. And we also use, in some cases, these gridded samples for strain analysis, where we take a sample, split it in 2, and put markers on it, which are spaced every 10 microns, so that we can then also analyze what happened to the rock during the deformation, correlated with the acoustic signals that we recorded. So first, let's look at the mechanical data. So those are stress strain curves here, and the individual color shows the confining pressure at which these experiments were done. So as you can see, at low confining pressures like 10 MPa, we typically increase the stress as we deform the rock. We reach some peak strength. Then we observe weakening, which is related to the development of the fault. And then we get to a new steady state stress level, which is basically governed by the frictional sliding on the developed fault. And as we increase the confining pressure, then the rocks get stronger and stronger. This weakening stops occurring, and eventually we have strain hardening that occurs over the whole range. If we plot the same data now in the Moore space, so here instead of strain versus differential stress, we'll be plotting normal stress versus shear stress. And we see that these are the individual Moore circles that correspond to these experiments shown here at left. And that allows us to construct a failure envelope, just as I was explaining you earlier, for this particular rock. And we can see that this failure envelope for Carrara marble intersects the Bayerle's law at about 62 MPa normal stress, so about 62 MPa, 60 MPa confining pressure. And if we go back to this plot that I was explaining you earlier, then we're basically exploring in these experiments sort of this range where we go from the fracturing envelope towards the semi-brittle flow field, and our differential stresses at 300 MPa are still higher than the confining pressure, so we don't reach entirely the brittle plastic transition. So let's look what the samples look like now after the experiment. So here, this is an example of these experiments after we take them out. So at 10 MPa, as expected, we have a large through-going fault, 25 as well, 50 as well. And at 75, we don't really see a clearly developed fault anymore. There's maybe a zone where strain is localizing. And then above that, there's basically no localization going on. So this nicely corresponds with the classical brittle-ductile transition, where we go from a developed fault to a distributed barreling in the samples. Now, we also can actively probe what is happening with the sample microstructure as the deformation is ongoing through the ultrasound pulsing. So because we have the sensors on top and bottom of the sample, then we can sort of measure how the VP velocity is evolving during these experiments. The VP, so that's the velocity of the P waves that go through, is dependent on the moduli of the rock and the density. And it can be therefore used as a proxy for damage that the rocks suffer. And so here, this is the stress strain curves that we have already looked at. And here is the corresponding VP velocity versus strain plotted. And so as you can see at low pressures, for example, here 10 MPa, we have a huge drop off in the velocity where we go from about 6 kilometers per second to below 4 kilometers per second that then stabilizes. Whereas as the pressure increases, then this decrease becomes more linear and much less pronounced. So there is less damage that would slow down the P waves as they go through the samples. And this has been analyzed extensively by Hilary Chang, who did a really great job by getting very precise measurements. The second data type that we can get from these experiments are acoustic emissions. So the velocities are basically measured that we send a known ultrasound pulse and we wait and record when it arrives. But in the meantime, when we're not pulsing, then we're just listening to the rock and trying to see if we can hear any defects. And we could record about 1,500 AEs from all the experiments. And then in order to quantify the types of the AEs, we use unsupervised learning methods to basically cluster the waveforms that we record and see where they occur. So what we use is so-called dynamic time warping method, which basically calculates the Euclidean distance between each waveform and quantifies their similarity by hierarchical clustering of these waveforms together. So we can then basically look at different levels and see how typical waveforms appear in the experiments. And this has been work that has spearheaded by Tushar Mittal. And so this is an example of the AE results. So here on the left side, we have now a stress strain curve in blue for an experiment that was conducted at 10 MPa confining pressure. That's what we already discussed. So this is the strength of the rock. We have the P wave velocity, which is shown here in red. That's what we also just discussed. And here the new information are these little kind of balls, which are the individual acoustic emissions. And they are now color-coded based on the cluster, which was assigned based on the clustering method that I just described. So we have clusters A, B, and C. And the characteristic waveforms that come from these individual clusters are shown here. So the yellow waveforms are these low frequency, low duration events, whereas the B and C are events which have a much sharper onset and typically also a much shorter duration. So this is what we get at 10 MPa confining pressure. So we have a lot of AEs, up to 400 AEs roughly that occur. And the typical duration of an acoustic emission is about 10 microseconds or even a little bit longer at these conditions. Now, if we look at what happens at 200 MPa confining pressure, so here we have considerably less acoustic emissions, around 110 or so. And the clusters here seem to be clustering closer together, where here essentially any acoustic emission can occur any time during the experiment. Here it tends to appear that most of these D and F clusters occur during the yielding, whereas the E cluster is initially dominant and then in the end. And the clusters here are quite different than at the lower pressure. And the biggest difference is basically in their duration. So here, if you look on the time that these acoustic emissions take or are active, it's only on the order of about a microsecond. So there's an order of magnitude in shrinking in the time scale of how these acoustic emissions are occurring. So the frequency is increasing as we're increasing the confining pressure. And now, if we take all the acoustic emissions from all the experiments, then we can try to basically tease out if there is some characteristic conditions under which the individual acoustic emissions are occurring. So this is a plot of a so-called distance matrix. So we essentially take all the waveforms that we recorded and we correlate them with each other. And here on the diagonal, that's basically a correlation of the waveform with itself. And then the more blue the color is, the more dissimilar those waveforms that you're comparing to are. And from that, we recover here these main 5 clusters that are shown here. So this would be cluster 1. Those are events that tend to occur at low differential stresses, low P-wave velocities, and generally at low strains and low confining pressures. And then we have these events in clusters 2 and 3 and 4 that sort of are these events which are much more impulsive and short, that have more and more of these high frequency overtones that kind of increases the pressure is increasing. And so we call these 2, 3, and 4 events the type 2 events because they have many similarities if you look at them, that it's basically a very abrupt onset and not too long waveform. We call this long duration, low frequency events type 1 clusters, which are typical for a low stress, low strain, and low VP and confining pressure. And at last, we have these type 3 events, which are essentially shown here. They are characteristic in experiments at high differential stresses, high VPs, and high confining pressures. And those are very high frequency events. So now if we look into the microstructures, so we see clearly that the characteristic of the acoustic emissions is changing as we're crossing the brittle-ductile transition. And so now we can look how the microstructures are changing as well. So we use this, this microscale strain mapping technique. So we image the rock before, so we know exactly what the rock looked like, how many twins there were, how many open cracks, which are mostly grain boundaries, were before there, and what their orientation was. And then we see how that rock changed as it deformed. So at 25 MPa confining pressure, where we see a development of a fault, can see that there's a abundant increase in microcracking, which is shown here in white. And these microcracks, excuse me, these microcracks are preferentially oriented parallel to the loading direction. So that tells us that those are mode 1 cracks. And all these red features, which are either twins or slip lines, tend to be oriented oblique to the loading direction at about 45 degrees. So that tells us that those are probably defects that are activated based on the maximal resolved shear stress. Excuse me. Now, if we look at the experiment that was conducted at 75 MPa confining pressure, so there's no macroscopic fault that developed, then we can see again that there's quite a bit of cracks, and they are again oriented in a similar orientation. So those are probably mostly mode 1 cracks, but there is a much higher density of the crystal plastic defects, which are shown in red, and and again, the orientation of these crystal plastic defects is consistent with the planes where the maximum shear stress is resolved. So we can quantify this roughly, and we can see that the amount of cracks is slightly decreasing as the pressure is increasing, whereas the density of the twins and slip lines is strongly increasing with increasing pressure, and as well as these zones of intense damage where basically it's impossible to figure out whether those are cracks or individual crystal plastic defects. So now if we want to tie all these measurements together, so we can try to see what we can learn about the defect dynamics of a brittle ductile transition. So we can use kinematic source models from seismology, which basically relate the frequency, the corner frequency of a recorded acoustic emission with the propagation velocity and the size of the defect. So here in this plot, we just show the frequency shift that is observed for all the experiments that are color-coded here based on their confining pressure and the cumulative probability. So what you can see that at 10 MPa, now the frequencies are below 1 megahertz, and as the confining pressure is increasing, then they steadily keep shifting to higher and higher higher frequencies. If we now calculate what it means for the size and speed of the defect, then we can see that the propagation of the defects versus the effective source dimension gives us basically isolines in the frequency space. So if we record an acoustic emission that is a 1 megahertz corner frequency, then that can be either caused by a very small source that is moving quite slow, or by a rather large source that is moving very fast. We have, of course, some constraints on how large our sample is and how fast the S waves are propagating in the sample. So we know that we must be somewhere in this regime, but without direct observation, it is difficult to exactly constrain what the size or velocity of these defects is. But what is clear is that as the pressure is increasing, then the defect size must be either decreasing or their propagation velocity must be increasing. And we can use one more additional information to try to constrain a little bit more where we are in this space, and that is the amplitude of the individual events. So if we add the amplitude information and account for attenuation, which is much more significant, of course, for higher frequencies, then we can see that the defects essentially that are forming the third type of defect, so those are the crystal plastic defects, they must be propagating quite fast and must be relatively large, because we can still record them and they should be very attenuative. Whereas the defects that are in the type 1 and type 2 that occur preferably at the lower pressures, they seem to have a slower propagation velocity, and in general, they decrease in their size. So the type 1 and 2 signals, they decrease in size and increase in propagation velocity as the pressure increases, whereas the type 3 signals, they must be increasing in size and velocity as the confining pressure is increasing. And to just validate whether this is something that is really possible, because generally when people record acoustic emissions, then they just think about cracking as a mechanism of generating those. But in material science, it's also quite commonly used to study the dislocation dynamics and twinning dynamics. And we did some additional experiments on single crystals of calcite that we also instrumented with a number of piezoelectric sensors. And here we just did a coaxial compression in the direction of these arrows. And we had a fast recording camera that was recording at 10,000 frames per second, so that we can observe optically how the defect propagates and then correlate it with the acoustic signatures. So this is an example of a twin that is propagating during the deformation. So you can see here, essentially, it will replay, I think, shortly, that there's this kind of feature that propagates from this side, and it hits here the existing twin. And then you can see these kind of colors changing, which is related to the twin thickening. And so this is clearly a twin, E-twin. We have also the EBSD data for that, so we can quantify that this is indeed a E-twin that is propagating. And here, this is an additional, this is an additional video that allows us to basically visualize the size of the source and what kind of acoustic emissions are occurring during this process. So it is clear that even crystal plastic defects as twins do have their acoustic signatures. And we can probably, using these clustering methods, we can distinguish the individual defects from each other. And so to conclude, I would like to first summarize the first part of the talk, that there are many models that implicitly are used to describe the brittle ductile transition over a range of time and length scales that are common to different disciplines. And the fact that the terminology is basically very confused really hampers the communication between the individual disciplines. The other thing that we have clearly documented and observed is that the microscale defects, so the fundamental agents of deformation, that they exhibit profound changes as the rocks cross a brittle ductile transition. And with the increasing pressure, the number of the acoustic emission decreases and their mean frequency increases, which implies that there is a decrease in the source size and increase in the propagation velocity of the individual defects. If we add this attenuation corrected amplitude, and we also see that the crystal plastic defects and the brittle defects have distinct trends, and the characteristic waveforms are likely caused by different defect types. So we can distinguish what are cracks, what are twins, and potentially what are dislocation avalanches, which allows us to see how their relative activity is changing. The microstructure document that the cooperation of fracturing and twinning and dislocation line in accommodating strain is very common in these rocks, basically over the whole range of pressures. And the cracking is suppressed, and twinning and dislocation avalanches get more pronounced as the pressure is increasing. We also observe complex hybrid events, which basically have signatures of both. So that suggests that the interaction between the defect types is very common. And the outlook that we're currently working on is that this is all done for marble, which is a very convenient material to study this brittle ductile transition. But of course, in nature, it is not the most important rock forming mineral. And we are developing currently high temperature sensors and new methods of AE detection and analysis so that we can do similar experiments also on in silicate rocks at much higher pressures and temperatures to study how their defects are evolving.